certainly do not grow like that. You grow whatever. So the question was, when is it convenient if you start from an arbitrary initial condition like that to progressively move, that is, choose x1, x2, x3, x4, and lambda 1, lambda 2, and c1, so that you approach this. Right? This problem can be posed in many ways. It can be posed as a terminal condition, can be posed as a utility maximization problem. I'm not going to discuss that. But there is a huge literature that was started by Samuelson, but then developed mostly by other, in particular again Mackenzie and Nikaido and Morishima and many other, that studied the problem, and it's called the turnpike problem. Okay? So for about 30 years people studied the conditions under which, with a constant technology, it's optimal, it's a good thing, or people, selfish people will, in a competitive market, there are two versions of it, right? The selfish people competitive market, the optimal planning problem, converge to the balanced growth, okay? I'm just mentioning it. If you're curious, there is a big literature there, okay? And the answer is, under certain condition you do, and under certain condition you don't. There is absolutely no reason to expect that you will go to balanced growth, okay? Even with constant technology. The intuition says that probably you will, because evidence seems to suggest that really stationary economies where nothing really happens, where technology is almost not changed, tend to become very repetitive. People tend to do more or less the same thing. But one thing is what you observe in history, one thing is what the model says. In the model, there are conditions, and basically when people are patient, they converge to the balanced growth, right? So if people are patient and plan for a very long period and the time horizon is very long, there will be the sequence, this will produce a sequence xt that will converge to x star in the limit, okay? That's the general form of the turnpike theory. There are many versions of it. I have worked on it, Schenkman has worked on it in the 70s, Brock, and many people. So, anyhow, this is pure theory. So, if you're interested, go look at it. Let's go back to our problem, okay? Balanced growth. So, why is this relevant? Well, it's relevant because it seems to say that the mystery of accumulation is not such a mystery. As long as the technology you employ is productive, and as long as relevant factors are reproducible, you can grow forever. All right? This is pure neoclassical theory without technological progress. It's what people now call AK, unfortunately. It's just all von Neumann, only trivialized. Now we have to ask a number of things. One thing is, why? Notice that this growth is endogenous in the sense that people use, in my opinion, incorrectly, endogenous these days, right? G depends on the technology, and depends on the impatience, and depends on the utility function, right? So why people asked about endogenous growth in the 80s? Okay? Two, How about TFP? What does TFP have to do with this? There's no TFP in my model. Well, in my model, for my model, right? Right? Three. Actually, we should maybe, this is a much simpler question, but it's relevant. Think how this economy grows. In this economy, population can be made constant. But if we make population constant, right, then population cannot be an input. So that makes you think. How about population, i.e. per capita income? Okay? Right? See what I mean? When we talk about growth, we can give it two meanings. One is growth in the total amount, where per capita income remains constant, but because population grows, everything grows together. And a second meaning is growth in per capita income. Population may or may not be constant, may or may not grow, but what matters is that the amount per capita also grows. Is it possible to have this in that model? This one? What do you think? Let's start from that question. Do you understand my question? What is that you need to do to take a model like this? For example, take the simple case in which population is constant. Okay, so population does not increase or decrease. How do you make human, I already said the answer. How do you make per capita income grow in a model like that?
Maybe we can view the human capital as an input and output, because we have constant population L, but each human has a human capital.
Exactly.
We can view it.
We have to start thinking and ask, does it make sense, does it not make sense? So you understand, it's an empirical issue, right? It's an empirical issue. If population is constant, may I have income per capita grow? Yes. And one says how? Well, because the workers becomes more and more skillful. Now you understand that at this point you're getting to a situation in which, so they accumulate more and more human capital, right? You become, the model becomes ambiguous, right? Because mathematically what we are describing actually, this is Uzawa, 1960 model. One of the many, Uzawa was one of the people that participated at that debate on the Turnpike. And he has a little example of the Uzawa model. If you read it, read please. By the way, you may not know, Hirofumi Uzawa and Charlie Koopmans were in eternal competition during those years. And so they brought a lot of parallel papers competing with each other. One from Stanford and the other at Yale. Okay? So Uzawa has this little model, which is a simple version of that, only has two sectors. But it's exactly like this. It's a special form of this. Okay? It's a special case. Where he actually addresses this and he says, look, population is constant, normalized to 1, but the factor of production is H. And I accumulate more of H. He uses Cobb-Douglas production functions that have H at the alpha, K at the 1 minus alpha, right? In one sector and in the other. But there's no technological change because they grow along a balanced growth path. And both factors grow. It's very simple. I'm sure you know how to do it. You see, it's constant return. The trick is all in constant return. Constant return, reproducible factor. In fact, the funny thing is, homework. Write a 2-sector model, or if you want 3-sector, up to you, of growth in income per capita due to the accumulation of physical and human capital, okay? Where the production functions are fixed coefficient. They're not Cobb-Douglas, they're fixed coefficient. So write Uzawa in the von Neumann format. It should be very easy. It's very simple, right? Just 2 rays, and you keep going on the rays. As long as the ratios are right, keep going. Right? So the substitutability doesn't really mean anything. The only thing that means that is relevant is linearity. Aggregate linearity in the two things. But what's the problem there? And here we go to next week's lecture. What's the problem? When we say more human capital, what do we really mean? You see, that's the problem. When we say more cows, we know what we mean. More cows. Same type cows, only instead of having 3, I have 4. Instead of having 4, I have 5. Instead of having 5, I have 6. Same damn cow. Same damn grass, same damn milk. Technology is the same. You just milk them the same way. You take them to the, you know. When I say I have more human capital, what does it mean? So I can have more skill at, you know, doing some jobs, mechanical job. Up to a limit, I can become more productive that way. I just train. It's like, you know, train, practice, practice, practice. You become a better basketball shooter by just shooting every day a lot. It's kind of same human capital. It's more productive, right? You make more points per minute. But that stuff, so that's constant technology, right? That stuff is very limited. That stuff always hit an upper bound. You can become the fastest assembly line worker on the damn universe. Eventually you stop for that given technology. Then they change the machine, then you change the machine, you make a different machine, you acquire the skill to manage the machine, and then you become 2 times more productive with less effort. And so we say, oh, you accumulate more human capital. Yes, but we also change human capital. That's the ambiguity. So using the notion of accumulating human capital in the, say, Uzawa format, that then many people have used since, right? Uzawa paper is almost 60-year-old. Right? So using it in that form, again, is useful for aggregate research. But one has to keep in mind that eventually that word, H, means change in technology. Right. And therefore that K is not the same K. Right? So the pilots that now fly the completely electronic 777 has more human capital than the pilots that used to fly the old Fokkers with propellers, right? And in fact is much more productive, carries many more people at a higher speed, less time, less risk, less crashes, everything, you know, much more productive. But it's not just reducing that to more human capital is a silly simplification because he's using a very different technology. all this human capital is specific to the new airplane. In fact, now people say the modern current pilots, are unable to fly those jets manually like in the old days. There's all debate. No, this is only partially true, as we have seen, if they're properly trained, right? But the essential thing is that it's a different technology. So the proper way to see it is that there is a pairing of kinds of human capital and kinds of capital, physical, that go together. Right? So this makes you think about what we mean here. Because the solution that we tend to give, the analytical solution to get growth in income per capita with a constant technology, is the one you propose. We do that. I do too. We all do it. It's a useful analytical tool. It's a simplification. You remember, models are false. They would not be models if they were not false. If they were true, they would be a parallel universe. Right? So models are always false. We simplify, make something false. Could be useful if we keep that in mind. That in fact it's a way of representing technological change. Right? So first problem we get from von Neumann story is, yes, sure, I can write a model like that, but it's hiding technological change, matter of fact. All right? You with me? Yeah. You got the lesson? Good. So no surprise. Utsawa, 1960, very clear. Very clear. Very clear. Absolutely clear. How about TFP? You remember how the TFP thing was brought about by Solow and many others, right? Rilke, Swan. What did they do? They said, look, I'm not going to have all this detailed thing. I'm just going to aggregate output and measure it in dollars. And call it $Y. And I'm going to compute its rate of change. You know what a rate of change is, right? YT plus 1 minus YT divided YT. Okay? And then I'm going to have physical capital in dollars too, constant, and compute its rate of change. And I have number of hours worked and also computed in rates of change. Right? If the technology was constant, these three things would be related in some form, right? In fact, here, they're very clearly related. If you compute TFP in this model, it's 0. Right? Yep. The growth rate of this is completely explained by the growth rate of the elements in here. In fact, it's lambda. They all grow at the rate, sorry, G. They all grow at the rate G, right? Yeah. And it adds up, right? It's alpha 1G plus alpha 2G plus alpha 3G plus alpha NG, where the sum of alpha 1 alpha 2 is 1, and so it's G times the sum of the alpha, it's 1. G. So G on the left, G on the right. So the point of the TFP research was, when we do this with the national income accounting data, we do not get equality, we get this. Now you say, Boldrin, why did you write alpha and beta? Because it doesn't really matter which weights you put. In the traditional literal, people have put the factor shares, but you can put any reasonable weight, trying to motivate with some structure of market form. If it is not competitive, you can put some physical weights that you think you can extract for input out. You pretty much get always the same residual. That is, you get that the growth of this is larger than the weighted sum of the growth of input. And what's the reason? The reason is that you measure in dollars, but they're different machines. You measure in hours, but they're different human beings. They embody different human capital. In fact, we know that we have a lot of micro research. I did that myself on Spanish firms, that if I break down that very carefully at the micro level, the first person that did this was Zvi Griliches, right? Zvi Griliches, in his PhD thesis, did this exercise on US agricultural sector and showed that you could eliminate the TFP residual by accounting carefully for the change in the type of machines and the change in the type of workers. That is, accounting for technological change, right? But if you don't, if you treat capital as if it were homogeneous and labor as if it were homogeneous, then there is a big residual. The thing that I thought was very relevant of that old literature and extremely important was, hey, look, technological change is very important.